Ladies and gentlemen, people with competition plans, all the BMT fans, I'm Ishwar from Outreach, and I'd like to present a problem from last year's BMT, Algebra Problem 7. So we are given three integers b, m, and t that are between 0 and 24, such that the cube root of b times m times t times the sum of b, m, and t equals bm plus mt plus bt. So the first thing that comes to mind from this is Vieta's formulas. And just to recap what that is, if we have a polynomial, x with roots b, m, and t, and let's say we can rewrite this polynomial in the expanded form, then p is the sum of the roots, q is the sums of products of pairs of these roots, and r is the product of the roots, and this can be derived by distributing this product. So what we're given here tells us that the cube root of r equals times p equals q. So you divide by p on both sides, and then cube both sides to get r is equal to q cubed over p cubed. From there, we can plug that in to this polynomial, try to factor it, and see what we get. We multiply by p cubed on all sides. Then we use a change of variables, u equals px, to get the following. Let's see if we can try to factor this. So looking at these two terms, we see that we can factor out a p squared and a u to get that this is p squared u times negative u plus q. And then we could look at these other two terms and say that we can also factor a u minus q out from there to get this term. And we see that u minus q divides both of these terms, and so divides the whole polynomial. That is, px minus q is a factor of this polynomial. And then that tells us that q over p is a root of the original polynomial over here. So let's try to plug that in into our factorized version up there. So we have q over p minus b, q over p minus m, q over p minus t equals 0. And the idea here is that if this is 0, then one of these three factors, after we substitute q and p in terms of b, m, and t, at least one of these three factors has to be equal to 0. And so we can solve for b, m, and t from there. Let's look at one of these terms and then generalize to the other two. Plugging in q and p gets us that bm plus mt plus bt divided by b plus m plus t minus b. And that's equal to, if we move b to the numerator, that's bm plus mt plus bt minus b squared minus bm minus bt divided by b plus m plus t. We can cancel out bt, bm, to get that this is equal to mt minus b squared over b plus m plus t. And that tells us that this entire expression is mt minus b squared times bt minus m squared times bm minus t squared over b plus m plus t squared cubed equals 0. So we can, because b, m, and t are all positive integers, we can multiply on both sides by b plus m plus t cubed and not add any additional solutions. We now see that at least one of these three factors has to be equal to 0. And that gives us the following relations. mt equals b squared, or bt is m squared, or bm equals t squared. And so one of the numbers is the geometric mean of the other two. And let's say we ordered these numbers and used this relation. That means that m is the middle number is the geometric mean of the other two numbers, and furthermore, that all three numbers form a geometric sequence. This tells us to do a little bit of casework. Okay, so there are two cases. b equals m equals t, and b is strictly less than m, which is strictly less than t. And so let's try to, for case number 2, we'll try to find all possible triples and then multiply those number of triples by 3 factorial to account for the different orders. And we add the number of triples we get from case 1. That will be our answer. So in the second case, the first thing to note is that t cannot be a prime. So that's because we know that t divides m squared, and since t is a prime, t divides m, and since m is strictly less than t, we know that that's a contradiction, so t just cannot be prime. So we can list out different values for t in a table like this. Right, and we also know that b times t has to be a perfect square, so let's try to search for those values. So for t equals 1, the only value for b that works is 1, but we're not counting that because we're in the second case and not the first case. For t equals 4, we see that b equals 1 does work because 1 times 4 is a perfect square, and we keep repeating this process. So we found 11 different triples, and so we multiply 11 times 3 factorial to get 66 different ordered triples such that b is less than m is less than t. And for the first case, there are 23 different numbers for b we can choose, and m and t would have to be the same number. So that is 23 additional ordered pairs. And adding those up gets us a grand total of 89. Thanks for listening. Have a great day.